By the end of this lesson, you should be able to state that transfer of heat during a change of phase does not cause a change in temperature. Define specific latent heat and state that L equals to Q over M. Observe the temperature. What happens to the temperature when ice melts? What happens to the temperature when ice melts? When ice melts, phase change from ice to water, the temperature stays the same. What happens to the heat supplied to the melting ice? The heat absorbed by the ice is used to change the potential energy and not to increase the kinetic energy. This heat is used to break the bond between the molecules. There is no increase in the average speed of the molecules. Hence, the temperature is unchanged during the phase transition. Without a rise in temperature, the heat required to bring about a change in state appears to be hidden or latent. This heat is known as the latent heat. When water is heated, the temperature of water increases and then stays constant when it boils. Why doesn't the temperature change even though heat is supplied to the water? During the change of phase from liquid to gas, the energy supplied is used to overcome the forces between the molecules. The heat supplied does not cause a change in the temperature. When water boils, steam is produced. Observe the temperature when all the water has been converted to steam. Ice at -10 degrees Celsius is allowed to melt and then is heated until it boils. Describe the different sections of the graph. Click on each region to know the changes taking place. From point L to M, water is in the solid state, ice. When heat is supplied, the temperature of the ice increases until it starts to melt at M. When ice is heated, its crystal lattice structure gains kinetic energy and starts vibrating vigorously. As the temperature increases, the kinetic energy of the molecules increases. At point M, the ice begins to melt. As the ice melts, the temperature of the ice and water mixture remains constant until all of the ice has melted at N. In the region Mn, ice and water coexist. At the melting point, the molecules get enough energy to break the bond and set themselves free from each other. Hence, there is no rise in temperature in the region Mn. The heat supplied is used to increase the molecule potential energy and not the kinetic energy. In the region NO, only liquid exists. The molecules receive heat and their average kinetic energy increases, and that causes the temperature to increase. At O, water begins to boil, converts to steam or gas. At the boiling point, the molecules that have received enough energy to overcome the attraction between the molecules escape to the gas. In the region OP, liquid and gas coexist. Hence, in the region OP, the temperature remains constant and the heat supplied is used to increase the molecule's potential energy and not the kinetic energy. Beyond the point P, heat supplied is used to increase the kinetic energy of the molecules. The temperature of the molecules increases and the molecules stay far apart, moving randomly. Observe the temperature time graph of water vapor being condensed and then solidified into ice. Click on each region to know the changes taking place. PQ is the region where water exists in a gaseous state, that is steam. The molecules are not bonded with each other, and so they are free to move randomly. At point Q, the molecules start coming closer to each other and forming water molecules. In this region, both water and gas coexist. The point Q is the condensation point of water vapor. The temperature remains constant and the heat loss is because of the decrease in the molecular potential energy of the molecules. The region RS in the graph is where water exists. As the temperature continues to drop, the water molecules slow down and move less freely inside the container. At point S, the water starts solidifying, thus at ST. The bond between molecules is stronger and some lattice structures begin to form. Water and ice coexist in the region ST. S is called the freezing point of water. In this region, there is no temperature change, as the heat energy lost is from the potential energy of the molecules, because of which they come closer to each other. As the temperature continues to drop, the ice is now below the freezing point. Molecules in ice are very closely packed in an orderly arrangement, and the vibrations of molecules become Ice melts when kept in open air or under sun. Ice absorbs heat from the surroundings. As the ice melts, its temperature remains constant. The specific latent heat is the heat absorbed or released per unit mass of substance when a substance changes phase at constant temperature. It is given as L equals to Q over M, where Q equals to heat absorbed or released by the substance in joules. M equals to mass of substance in kilogram. The SI unit of specific latent heat is joule per kilogram. If 2 kilograms of ice melts when 452,000 joules of heat energy is supplied to it, what is the specific latent heat of ice? Specific latent heat of ice. L equals to Q over M equals to 452,000 joules over 2 kilograms equals to 226,000 joules per kilogram.
This is a simulation to determine the melting point of wax. Click on the Start button to heat the candle wax in the boiling tube. At what temperature does the wax start melting? From the graph, the melting point of wax is 49 degrees Celsius. Melting point is the temperature at which the solid wax starts melting, so there is a phase transition. During change of phase, there is no temperature change. This is a simulation to determine the freezing point of wax. Click on the Start button to cool the wax. At what temperature does the wax start solidifying? From the graph, the wax starts solidifying at 49 degrees Celsius. At this temperature, the wax undergoes a phase change, and thus there is no temperature change.